All right, let's go on and talk a little bit about connecting capacitors. Usually, when we want to get a desired value for a bunch of capacitors, we go ahead and we connect them in two ways. We either connect them as a series circuit or we connect them in parallel with each other. So the way they look is if you connect them in series, they basically have these capacitors that are connected along the same path. This is, for example, C1, this is C2, and this is C3. Let's say you want to find the equivalent capacitance of these three capacitors. All you have to do is you have to say the total capacitance is simply 1 over C1 plus 1 over C2 plus 1 over C3 raised to the negative power. So what you do is you add them as a bunch of fractions, and then you reverse the answer. You take the reciprocal of the answer either in your calculator or by yourself. Now, if a bunch of capacitors are connected in parallel, let's say, for example, we have 3 capacitors, they will look something like this. Usually the trick is to just figure out if the capacitors are connected in parallel or series, especially in the more complex circuits. But anyways, if you want to find out the total capacitance here, all you have to do is add C1 to C2 plus C3. So if capacitors are connected in parallel with each other, you can find out the equivalent or the total capacitance in a much easier way because all you have to do is just add them. As an example, in the first one, if I have 2 capacitors, one with a value of 2 microfarads and the other one with 4 microfarads, if I want to find the total capacitance here, all I have to do is add 1 over 2 to 1 over 4 and then raise it to the negative power. Now I know that 1 over 2 is technically just 2 over 4, and 2 over 4 plus 1 over 4 gives us 3 over 4, and 3 over 4 raised to the negative power gives us a value of 4 over 3 microfarads once you flip the answer. Now let's say we had the same exact 2 capacitors, but this time they were connected in a parallel configuration. It would look something like this. So you would have a 2 microfarad capacitor here and the 4 microfarad capacitor here. The total capacitance is simply going to be 2 plus 4, and that's just 6 microfarads. Done and dusted. Now, let's go ahead and take a look at some more difficult examples to get a better understanding of how we can find the equivalent capacitance. Consider the circuit below. Imagine we have a circuit that looks like this. So the capacitors are connected in the following configuration. Let's say this one is 3 farads, 4 farads, this one is 5 farads, and this one is just 6 farads. There's 2 ways you can do this. Either you can name them one by one and then collectively just add up the names and see if they're parallel or kind of series with each other, or you can do it like without having to name any of the capacitors. So over here, obviously, if I name this one C1, this one C2, C3, and C4, C1 and C2 are in series with each other. So I have to say 1 over 3 plus 1 over 4 raised to the negative power. Now, I know that 1 over 3 plus 1 over 4 is going to add up to 7 over 12. So the equivalent capacitance for the first 2 are actually going to be 12 over 7, which in decimal format is simply going to be 1.7 farads. Now, the 2 bottom capacitors, on the other hand, they're also in series, but the way we can find them is like this. We can say C3 and 4, which means the capacitance of the 3rd and 4th capacitor are simply going to be 1 over 5 plus 1 over 6 raised to the negative power. And 1 over 5 plus 1 over 6 is going to give us 11 over 30. If we reverse that, we get 30 over 11, and 30 over 11 is simply going to be 2.7. So once you kind of add up the 2 capacitors on the bottom in series, you get a equivalent capacitor that kind of looks like this. So you have this capacitor here at a capacitance of 1.7 farads. That's the result of C1 and C2. And then you have another one on the bottom with a capacitance of 2.7 farads. Now, if we were to go ahead and find the total equivalent capacitance at the end, C total is simply 1.7 plus 2.7, which adds up to essentially 4.4 farads. That's how you find the equivalent capacitance in such a circuit. Now let's go ahead and take a look at another example. Let's say, for example, we have this configuration. We have point A here, and then the circuit sort of gets separated into the following capacitors. We have a 12 microfarad capacitor here that are connected across these 6 microfarad capacitors, again with a separate junction, and then another 6 microfarad capacitor, and this one goes down. Here we have the other end, B, and then we have a 12 microfarad capacitor at the bottom side here. So we can just say that's how our circuit looks. Now, if we want to find the equivalent capacitance of this capacitor here, all we have to do is this. First, we know that 6 microfarads and 6 microfarads are parallel with each other. So we can just add them very easily and say the resultant of that is just 12 microfarads. What you'll have after that is a circuit that looks sort of like this. So you have the top circuit with 2 capacitors at a value of 12 microfarads. And these 12 microfarads are essentially in parallel with the one on the bottom side, which is also 12 microfarads. I forgot to write that. Now, what's going to happen is these two at the top, these two capacitors at the top, are actually in series with each other. So in order to find their total capacitance, all we have to do is say that 1 over 12 plus another 1 over 12 raised to the negative power. Well, that gives us 2 over 12, and if we were to reverse that, we get 12 over 2, which is 6 microfarads. The 6 microfarads is then in a parallel combination with the 12 microfarads on the bottom side. So you have a 6 microfarad capacitor and a 12 microfarad capacitor at the bottom, which means the total capacitance is just the result of these two added up. 6 microfarads plus 12 microfarads, which technically will add up to a total capacitance of 18 microfarads. Now, usually what will happen is if we were to connect this, combination of capacitors to a battery, each of them would have a different voltage or different, for example, charge, and then we can go ahead and do the different calculations for that depending on whether they're connected in series or parallel. But for today, I think that's good enough. Thank you for watching, and the best of luck.